Thank you for joining BlackBag's Ask the Expert webinar series. My name is Ashley Hernandez, and I am the Director of Product at BlackBag Technologies. Today, we are excited to present the APFS Ask the Expert series. We've had numerous questions from our customers and Mac forensic users on APFS, and I'm excited to introduce Dr. Joe Sylve, who's going to be walking us through some of the common questions that we get asked, and also covering what we are going to be providing users in way of support in both our recently released MacQuisition 2018 R1 and the soon to be released BlackLight 2018 R1. So I would like to introduce you to Dr. Joe Sylve.
Hi, thank you, Ashley. My name is Joe Sylve. I'm the Director of Research and Development at BlackBag Technologies. And today we'll talk a little bit about the Apple file system, or APFS, which is going to be the replacement, or is now the replacement, for HFS Plus. So we'll cover a broad range of topics, such as why do we have and deal with a new file system in the first place? Which devices will we find this APFS file system on? What are the features of the file system at a higher level? And how do I identify and work with devices that use APFS? And then finally, we'll go into a little bit about what is the implication to us as investigators for having this new file system. Just a little bit of a history lesson here. Apple's first major file system came out in 1985, which was HFS. In 1998, they released an entirely new file system, which was based off of HFS, called HFS Plus. Very recently, at the end of 2007, Apple has transitioned over to a brand new file system called the Apple File System, or APFS. Work started in this in 2014. And it's intended to support file system across devices: macOS, iOS, watchOS, tvOS. It's completely new implementation and has some interesting features which we'll talk about. So which devices will you find APFS on? So all iOS devices after 10.3 and above, even if you had a device that had HFS Plus on it before and you upgraded to 10.3, the file system would automatically be upgraded to APFS silently. Any Mac shipped with macOS 10.13, High Sierra and above, and some systems that were upgraded to macOS 10.13, specifically machines with solid-state hard drives in them. In these cases, the file system will be silently converted from HFS Plus to APFS, even if core storage is enabled. And all devices going forward would mostly have APFS on it, and that includes Apple TV, Apple Watch, etc. The exception to this is Fusion drives. It seems that Apple was having some problems with APFS on Fusion drives. So Fusion drives and traditional hard drives are not automatically updated to APFS upon upgrade. So why did Apple decide to have a new file system in the first place? Well, from the information they've told us and the information we can gather based off of studying the file system, there is some improved performance. It does offer native encryption, better space management, improved versioning and backup built in, and it supports other modern file system norms like sparse files, nanosecond timestamps, fast directory styling, and native extended attributes. While HFS Plus may have had some or all of these features, they were mostly added on after the fact as an afterthought, and they were kind of hacks. APFS is a brand new file system that was designed from scratch and has first-class support for all of these features. The first feature we'll talk about is that APFS actually uses 64-bit integers for inode numbers. Now, while we might have had 4 billion plus possible files before, now we have 9 quintillion. And while we're unlikely to actually need that many files, forensically, this means for us that there should be, hopefully, less reuse of inode numbers. because we have so many inode numbers available to us, we can see that there would be very little opportunity for those numbers to wrap around and be reassigned. This was a need just to kind of future-proof the file system, and it also helps support some other features such as cloning and snapshot capabilities, which we'll talk about next. Clones allow instantaneous copy of a file or directory. So basically, if you try to copy and paste a file using the Finder GUI, rather than creating a brand new file, new metadata will be created, but that file's metadata will point to the same blocks as the original store. If you change a byte on that file, then those original blocks will be copied on write, and then you'll have another copy of the file on the disk. The original file and the clone contents do use the same blocks, but they're treated as separate files. And this helps us prevent data duplication and really minimize the storage use. We'll show you an example of this. We have a very small volume with basically one file here, this tool.dmg. And if you look at the info, you'll notice that there is a capacity of 104.8 megabytes, and you have 63.7 megabytes available. So if we make a copy of this file, you'll notice that those statistics don't change. Even though we now have two files, because those files have the identical content, the file system doesn't change. Now, as far as we can tell in our research, this only happens when you make a direct copy of a file. If you happen to create a second file with the exact same data as an existing file on disk, that data will be duplicated on the disk.
Joe, we do have a question on clones, and one of the questions regarding clones is, can I tell the difference between the original file and the clone by any of the metadata or other structures?
To my knowledge, no. The metadata looks pretty similar to any metadata of a file. You could probably do some deep analysis to figure out if any one of these files have pointing to the exact same blocks, and then by looking at the creation timestamps in the metadata, you could probably infer which was the original. However, I'm not quite sure of the forensic value in this.
All right, and then one more question regarding the previous topic when we were talking about inodes, and now that we have 64-bit inode numbers, with the less reuse of inode numbers, the question is, does Apple wipe the inode entry upon deletion in any way?
Not directly. We'll talk about that a little bit when we get into the copy on write semantics of the file system. But there is no direct zeroing out of metadata when a file is deleted. Are there any further questions at this point before we move on? One more
actually. If you make a copy of a copy, so if you make a clone of a clone, is the naming convention still going to be the same? Meaning it would be like tools copy, and then tools copy copy. And does the operating system still handle that the way it would have handled it before?
Yes, the naming convention is just a side effect of the UI Finder. You can rename these clones to anything you like, and they still behave the same way. But yes, you can have clones of clones. There's no difference.
Awesome. I think that's all the questions for now.
Great. The next feature we'll talk about is snapshots. The file system actually has a built-in backup mechanism, which is nice. Snapshots allow users to restore files on their system to a previous state. They're basically read-only copies of the APFS volumes, and they're created instantly. How they work under the hood is snapshots preserve file and metadata blocks at the time of the snapshots, so that they're not released back to the pool when this file is changed or deleted. A user is going to have the capabilities of saying, I want to revert back to my file system at a specific time, for where they either took a snapshot manually or through some automated process such as Time Machine. Right now, it doesn't seem that Time Machine is taking advantage of APFS snapshots directly on external disks, but we can see that they may be going in that direction. Finally, the final feature we'll talk about is the APFS has actually built-in first-class support for native encryption. Historically, Mac OS X HFS Plus did not come with full disk encryption support. This was not really a priority in the late 90s. However, as it became there was a need for it, Apple had some ways of handling this. They introduced core storage, which was kind of a virtual volume system that basically encrypted everything at the volume level. So rather than having support for encryption in HFS, they added a layer of encryption around it so that if you were going to mount the volume itself, the volume would be encrypted. Now, once you mounted the encrypted volume, a synthesized device would be created, which would have a logical unencrypted version of that file system on it. And if you've ever had to image Macs, you may have tried to acquire this device, and this device will give you a complete unencrypted version of the file system. On iOS, they decided to handle things differently. It's still HFS Plus, but it was a small variant of HFS Plus, which allowed file-level encryption keys and hardware acceleration. So now none of the file system metadata was really encrypted, but just some of the contents. This file data blocks were encrypted with a per file key. Now iOS and Mac OS X, if you're using HFS, if you're using APFS, has encryption built in at the file system level. First class support, which means that we will actually have all of the metadata as well as the file contents encrypted, and you can encrypt them with any number of different keys. Before we move into the APFS disk structure and the theory, are there any questions?
We did have one more follow-up on clones. I know clones are a popular topic because it's something new. And so with clones, what happens if you modify the original file? Does the modification reflect in the clone?
It will not. All of these clones are basically treated as copy on write. So if you make a change on any one of these individual files, they are not like hard links. If you make a change in any one of these individual files, a different copy of the file's data will be created and assigned to the file that you made changes to.
So you could end up with deltas from the original file in the first copy and then deltas for the original file as that file changes as well. Is that
it's unclear to me that if they're actual deltas or if you're just completely assigning all of the blocks new as copy on write. That probably depends on whether some of the extents are the same and some are not. More research is needed for that.
Great. And I think that's all the questions before we move on to the disk structure.
All right. So this is going to talk about more of the higher level structure of APFS. We do have information about the actual on-disk structures, which we can get into if necessary. So the first structure we're going to talk about is an APFS container. So a container is a logical store that can be made up of one or more physical stores. And a physical store is simply a disk or a partition. We're used to this notion of having one file system per partition, and these file systems would be of fixed size. APFS is a pooled file storage system, which means we actually are taking one or more physical stores together, and those physical storage blocks will be shared among one or more pool volumes. The APFS container is going to be identified by its own block device. So you might, even if you only have one physical store, you'll have a separate block device, which is this logical concatenation of the physical stores. You can image either the physical stores themselves or the APFS container. And only one, if you have multiple physical devices, you really do need all of the physical stores to rebuild the container, and only one of them is going to identify as the container device itself. So I mentioned that APFS is a pooled file storage system. So what that means is you can actually have very many lightweight volumes, and you don't have to specify the size of these volumes ahead of time. So previously, if you wanted to have multiple volumes, you'd have to take your disk and partition it. Say, for instance, I'm going to assign 60 gigs to volume 1 and 40 gigs to volume 2. And if I wanted to add a third volume, we would have had to repartition and resize all of these different volumes, which actually might lead to some loss of data. APFS actually has a very lightweight notion of volumes, where volumes only take up as much space as they need, and they grow and shrink as they need. So as you create files on a volume, they will take blocks from the free space in the container itself. And if you delete these files, these blocks will be eventually released back into the volume pool itself. So this notion of free space, we no longer have a notion of free space for a specific volume, because a volume is only assigned the blocks that it's using. The free space is actually going to be shared among all the volumes in the container.
I do have a question on this one for you, Joe, which is, does that mean that a volume space is not contiguous, meaning it could add space? And I know that you mentioned earlier it's kind of designed for SSDs, but does that mean a volume's allocated space could be all across that SSD? You know, it's not how we would have thought with traditional hard drives where it just grows in kind of fixed segments.
Absolutely. A volume space is no longer contiguous. A volume, the APFS container is almost a file system in itself, as where these volumes can grow and shrink. And the volume, the blocks that are assigned to a volume will not necessarily be contiguous on disk. And most of the time they will not be. Which is why we no longer are able to read from a specific block device for each volumes. There will be block devices created for these volumes, such as if the container was given, the synthesized container was given the notion of being, you know, dev/disk1, you will still get a dev/disk1 S0, S1, S2, etc. for each of the volumes. But those block devices aren't actually readable. And the reason for that is certainly because the blocks are not contiguous on disk.
Great, that covers the questions on the volumes that we have so far.
So a little bit more of a visual example here, where we can see here we have the storage, and we have two volumes in this one container. One is the Macintosh HD, and the second here is media. And what you can see here is there's the gray space is showing the space is being used for that specific volume. The white space with the kind of gray lines is showing that space that is not available on our physical store because it's being used by other volumes. And then the white space is showing that these are space that is available to both volumes. So the limited, size limitation for these volumes to grow is only limited by the space that is not assigned to any other device. Because volumes are so lightweight, I would not be surprised if we start seeing more and more of them. Right now, when you upgrade to 10.13 and your HFS file system is switched over, you'll see a notion of 4 different volumes being created. And these volumes can be mounted at any point in the file system. But because volumes support different levels of encryption, I would not be surprised if you start seeing a different volume for every user on the system. And each of these volumes can actually have different storage keys. That's not how it's implemented currently, but because volumes are so lightweight, things may be going in that direction. Are there any questions about the pool storage before we go into the forensics implications?
Not at this time.
So the first obvious implication to analyzing a pool storage file system is going to affect our file carving. While there is still notion of blocks that are allocated and unallocated, again, individual volumes don't have unallocated blocks associated with them. When you delete a file on a volume, those blocks from that file are released into the pool itself. So they'll be released in the container and can be used by any number of volumes that need space. So we can still carve on these unallocated blocks. We can still parse through the metadata for the container and figure out which blocks are currently assigned and which aren't, and still do file carving on those. However, the results that we find, we will not necessarily be able to tie them to a specific volume, because these blocks are now shared and there's no longer any metadata that is easy accessible to say which one of these volumes actually released this block back into the pool, because our volumes are going to grow and shrink as needed. So file carving is still a possibility. There does not seem to be any sort of secure deletion of files by default. However, we're not going to be able to carve per volume. So if we have very many volumes on a store, the data that we're carving out of is not going to necessarily be associated to a particular volume. And we can see that the more volumes that we have, for instance, if they decide to make a volume for each individual user, this will be more and more of a problem.
Joe, are there any boundaries on the block level, or is there no block level kind of boundaries that we have?
I'm not sure what you specifically mean by boundaries, but block sizes are 4K in length, and that is the smallest delineation that will be assigned. So the pool will never assign a block smaller than 4K, and if you need more space than that, it'll assign multiple blocks.
Perfect, that answers the question.
APFS uses strong copy on write semantics for its file system metadata, which means when an object is updated, and by object I mean one of these 4K blocks, an entirely new 4K block is created and referenced. So the existing block, if you even update, say, a timestamp for the metadata, it's not going to change that one timestamp that is existing at the same offset in the file system. It's going to create an entirely different copy of that 4K block with the different changes, and then updates its references to point to this new block. So this means, this has several forensic implications for us. It means we should be able to still scan for these old objects, which means we might be able to get information, recoverable metadata, and even file contents from older versions of files. However, even trivial operations, because of this copyright, means we're overwriting at least 4K on disk. Now, this doesn't necessarily mean that every time you access a file, because a file system access time is, we're overwriting 4Ks on disk. The file system likely has a way of pulling these updates and periodically flushing to disk, but we have found that simply deleting a directory of files does overwrite quite a bit of data on disk. Snapshots. With the advent of snapshots, this means that we'll have objects from points in times will be locked, which means even if those files are changed or deleted, the old blocks will not be released into the pool for use. So this makes it possible to reconstruct the entire historical volume state at the block level at the time of the snapshots. So those of you who are familiar with NTFS volume shadow copies, you're going to get something a little bit more similar to that, where you're getting the entire file system, including the metadata, rather than how Mac Time Machine backups currently worked with HFS Plus, where it's mostly just different copies of the data at the file level and some hard links to reconstruct the state of the file system.
Joe, do we know if snapshots are enabled by default with APFS?
Snapshots are not something that you have to specifically enable. It's something that has to be triggered manually by a user, but we have seen snapshots being triggered in some cases, such as local backups. We do need to do a little bit more researches to see exactly when they're triggered automatically and under which conditions. But it's not something that's optional, that you have to specifically go in and enable. But it doesn't also seem to be something that, you know, every week a snapshot is created, as far as we can tell.
We have a few more questions on snapshots. How does a user access or restore snapshots? Is there a specific area that they do that with?
Yes, unfortunately we don't have any screenshots of that, but it can be done using the built-in GUI. Okay, moving on. Block devices. So APFS created block devices behave a little bit differently than what we're used to. We're used to having a block device for the physical disk and a slice device for our physical partitions. We still have those, but in addition, we have a synthesized block device for a container. So if you have multiple physical stores, if you have multiple physical partitions, you can either image all of these things together, and your software will have to be able to put them together logically, or you can image this synthesized block device, which is going to be the logical concatenation of the container. That might be the better approach, especially for fusion drives and other drives that may have multiple physical partitions on them at a time. There are slice devices created for each of the individual APFS volumes, but they're not readable. And this becomes more of an issue once we start talking about encryption. Because encryption is now handled at the APFS object level. So it's built into the file system and not just a volume wrapper. So with core storage, what we were able to do, where you could mount this volume, and even if your forensic software didn't have any sort of notion of how to natively decrypt core storage, you could mount the core storage volume, image the logical decrypted partition, and then it's the same as if you would have had an unencrypted HFS plus file system. APFS doesn't work like that. There is no block device which can be read to get the unencrypted version of a volume. So our tools actually need to know how to read APFS encrypted volumes. We've noticed that there are slight differences depending on how this encryption is implemented versus depending on the scenario. The three scenarios we have identified, or if you just format a new disk and you choose APFS encrypted and it's going to prompt you for a password at that point in time, there will be a single volume key created, and as well as a backup key. So you have one password and a backup key that you can use to unlock these volumes. The other option here is if you enable File Vault, it works somewhat differently, where rather than having just one key, master key for the entire volume, these keys will be wrapped with an additional layer for each individual user on the system, as well as a recovery key. If you had a system that used core storage, HFS plus core storage full disk encryption, like File Vault was enabled, and then you upgrade it to APFS, the encryption is handled a little bit differently. Rather than having, you still have multiple keys for levels, but rather than decrypting each of these individual blocks for core storage encryption and re-encrypting them with the APFS encryption, it just uses the same methods of encryption that core storage used. These are all three of these scenarios are supported in BlackLight as well as MacQuisition. So before we go into what it looks like in the tools, are there any questions about how this might affect you forensically?
So there is a question that, and I think we're going to talk about this as we go into how they work in the tools, but MacQuisition does allow imaging of the APFS container, or they're referring it to as the synthesized container. Will BlackLight 2018 R1 now be able to ingest and parse these images?
Yes, it will. You can ingest either the physical device or the synthesized container.
And then I do have one more question. If a file is deleted, this is back to our snapshots, do all the related snapshots get deleted also?
If a file is deleted and you have snapshots, the old versions of the metadata of that file still exist on the file system. I think what I was trying to explain when my internet connection dropped is that there's this notion of B trees that store the file system metadata. And these B trees each have objects in them, and these objects have object IDs and version IDs. So when you take a snapshot, what happens is the old version of that object stays along in the B trees, and the new version will be created with just an updated version number. So the latest version of the file system is only going to show you the newest version of the metadata or those file blocks. If you delete that file, that object metadata might be deleted. However, the old version of that file's metadata, because you have a snapshot on the system, will remain unless that snapshot is deleted, and then perhaps it will be deleted. Does that answer the question, Ashley?
It does. And I have a few more questions about what's going to be supported in BlackLight and MacQuisition, but we will cover those as we go through the next section. So I'm going to hold those, and then if you still have questions after we go through what it looks like in MacQuisition and in BlackLight, then we'll cover those at the end. So go ahead and move forward.
Great. So MacQuisition 2018 R1 has been released. I believe it was released earlier this week or last week. So this is available now. Has full support for APFS encryption, APFS acquisition, as well as encrypted containers. So first I want to mention that you'll notice that a disk is marked as encrypted here in red. So it seems pretty obvious. You do not need to decrypt these containers to take images, and you do not need to decrypt them necessarily at this stage to bring them into BlackLight and analyze them. But if you would like to use some of the functionality of MacQuisition that allows you to kind of triage and collect logical files, you obviously need to unlock them at this point. You can choose to unlock a volume either via the password or the recovery key, and that is true both in MacQuisition and in BlackLight. Either one will work. And then you'll notice that we successfully unlocked this volume. At this point, you should be able to use all the various functionality in MacQuisition you would normally use for triage and logical acquisition. Still going to select our image device to acquire, and everything will work as you're familiar with MacQuisition. You'll notice here, because we've unlocked the disk, we're able to see individual logical files and the address book and the chat messages, et cetera, et cetera. Again, if you just want to take a physical image of the disk and you don't necessarily have the password at the time that you're doing acquisition, that's fine. You can still acquire the encrypted version, and when you bring it into BlackLight, if you have the password at that point, then we can actually do our file system analysis on it. This allows you to do logical acquisition as well. Yes.
A couple of clarifications. One is bringing those encrypted images into BlackLight. Could we do that on a Windows or Mac machine for the APFS encryption?
Yes, BlackLight actually has first-class support for APFS, including encryption. We're not using any file system APIs. We've completely reverse engineered the file system and done our own implementation. So everything that I'm talking about on the BlackLight side will work just as well on Windows as it will in macOS.
All right, and then another question is, so do we image disk 0 or disk 1 when we're looking at MacQuisition, or does it even matter?
It doesn't matter. You can image either one of those, and they will be adjusted by BlackLight. My recommendation would be, if you have a Fusion drive, which has or any other drive that has multiple physical stores, you should image the logical synthesized disk, the container itself. This is going to make you be able to analyze that in today's version, 2018 R1 of BlackLight. I say today's version; it'll actually be released in the next week or two. However, the initial version will not have support for multiple physical stores. Now, so in that sense, you're always going to be able to ingest a synthesized container, so you probably should take that. However, if there are other volumes on the disk that you may be interested in, other physical partitions on the disk, then the physical image may be of use to you as well.
Great, and just of note, with MacQuisition 2018 R1, we did add a couple other features. One is you can now export these to NTFS formatted destination drives, and also for the logical collection like you're doing here, you can now actually create a Mac sparse image with those. So I did want to note those before we move on. I think next is going to be talking about what it looks like in BlackLight.
Yes. So APFS support in BlackLight is not going to be entirely different than what you're used to. The file system itself doesn't necessarily impact the same sort of file level artifacts that you're familiar with. So if you're upgrading from HFS Plus, all the same stuff will still be there, FS events and logs and all of the goodies that we're able to parse in BlackLight. However, because of the notion of pool storage, we did have to make a few changes in our UI that are specific to APFS, and those are the ones I'm going to talk about today. So here you notice that we're bringing in an APFS image, and this is an image of a physical disk. So we still see all of the different physical partitions, the FAT32 EFI partition. This one actually has a physical NTFS partition. But you'll notice this new gray box. This new gray box here represents the logical APFS container. So all of the partitions that you're seeing inside of here are actually the APFS volumes. And you'll see that the APFS volumes, you have your individual sizes of these volumes, and these are the sizes that are being used. And you'll have the one unallocated device, which is going to be the unallocated space that allow you to carve on that container itself. Because the individual APFS pool volumes themselves don't have any unallocated space associated with them, you'll notice that all our file carving will be disabled for the individual volumes. However, you can still carve across the container by importing that unallocated APFS partition there. If you try to ingest an image with an encrypted volume on it, it'll look much the same. However, the volume will not be selected by default. You'll notice that next to the size, you'll see it just says that it's encrypted. And if you click on the little box next to the encrypted volume, what you'll get is a password prompt that looks similar like this. If there's a password hint, that will be shown to you, which may help you guess the password itself. And here, if it's a file vault encrypted volume, you can enter the password of any one of the users, and any one of them will work, or the recovery key itself. If it's upgraded from core storage, the same thing applies. And if it's just an APFS encrypted volume that only has one password, you would have to enter the password or the recovery key.
Joe, I do have one question about
yes.
the prompt for encryption. So we do have encryption support now natively built into MacQuisition 2018 R1, but what if they had imaged an APFS encrypted drive with MacQuisition prior versions like 2017 R1 and they have that encrypted disk? Will BlackLight 2018 be able to read those older files and prompt them like we're seeing here?
If it is an APFS encrypted drive and you just have a physical disk image, yes, you should still be able to import it into BlackLight.
Thank you.
This screen here also will give you immediate feedback whether the disk can be unlocked. If you put the wrong password in, you click unlocked, it'll prompt you again. We cannot and do not try to import encrypted volume without the password because we can get no information from it. Even the metadata itself is encrypted. And one minor change that we've made so far to the UI is just in the details view. This is a small change, but it's worth mentioning. If you notice here for non-APFS file systems, for instance, this is the EFI partition, which is a FAT32. You'll see that you get both the space used here and the space available. Because it's FAT32, there is some free space associated with the volume. But APFS volumes don't necessarily have free space associated with them, so it didn't make sense for us to do the same thing. So what we do is slightly different. We only show the space used for the volume, and you'll get a new notion here of how much space is the total size of the pool container itself. That's a minor change, but it's just worth mentioning. So in review, the APF file system is found on many upgraded iOS and macOS devices and all new ones going forward from September 2017. It does have some new interesting features such as snapshots and clones and copy on write, which may offer us more file history to reconstruct activity once we start doing further analysis. APFS containers can have multiple volumes that share free space and share blocks that grow and shrink. So items found in unallocated space are going to be harder to attribute to a specific volume and possibly a specific user. And MacQuisition in the upcoming BlackLight release will acquire, decrypt, and process APFS volumes. Well, for BlackLight, of course, is Windows and OS X, Mac OS. Are there any further questions?
We do have a couple. Have you noticed any processing impact when processing an encrypted APFS container versus one that was decrypted during imaging? I know we had a note on the slide about there's no real difference between the two, but have you seen anything different when processing as far as maybe speed?
There is no difference. The only reason to unlock the disk in the MacQuisition side is if you want to do some of this logical collection or you want to use some of the triage features. That's just you're unlocking it to allow MacQuisition access to the logical data. If you're still taking a physical image of the disk, it's going to behave no differently in BlackLight or not. And that's because, again, all this data is encrypted at rest on the disk at the file system level. So just simply unlocking it in BlackLight, you're not imaging anything different than you'd be imaging if that device was unlocked. This is not the case, for instance, for HFS Plus core storage.
Great. We do have a couple questions about the ability to gain access without a password or recovery key or references to brute forcing. My understanding, Joe, is we don't have that built into our product, but I don't know if you're aware of any other tools that provide that functionality right now that you can mention.
I'm currently not aware of any tools that provide that functionality. However, my analysis of the file system suggests that this should be very possible. All the information you need to decrypt, to brute force the key is available without the password itself, and you could do some sort of offline brute forcing. However, it does use industry standard techniques, key wrapping with variable length iterations and salted, so the brute forcing will be slow. And I'm not aware of any tools that currently do this, but it's technically not impossible. The one caveat for that is the new iMac Pro with the built-in T2 chip. That seems to handle things a bit differently, where you're actually doing some sort of hardware level encryption as well. Those keys probably cannot be brute forced outside of the device itself.
All right, so I think that's the time we have for questions right now. There are additional questions that, like I mentioned, if we didn't get to your question, we'll make sure to follow up with you after the webinar. I did want to reiterate, if you are interested in the MacQuisition functionality, that is available today. So 2018 R1 will acquire both encrypted or in a decrypted state, those MacQuisition evidence, those APFS evidence files creation for you. And then there were many questions about when are we going to get BlackLight 2018 R1 into your hot little hands. So we are working on that diligently. Like I said, it's in beta right now with a few folks, and we're putting the final polish on it. We expect to have it out in the next week or so. So follow us on social media if you want to keep track of that, or if you're already own BlackLight, look for an email in the next week or two announcing the release of that APFS support. So that'll be full support. You can bring in encrypted images and it will prompt you for the password, or you can bring in unencrypted images created by MacQuisition 2018 R1. Both of those are fully supported. And we'll continue to look to Joe and his research as we find new and exciting things to report to you guys on APFS. We'll continue to provide these webinars on topics like this and similar topics. So if you have a suggestion or request, you can at Joe or I on Twitter. Mine is Ashley BFIR, my handle there. And Joe's also available on Twitter for you. I think you were on the last slide if you want to give your Twitter.
It's at SYLVE. But Ashley, if they have any further questions, either about the product or technical questions about APFS, what is the best way for them to ask those after this webinar? So
you can always ask questions on our product support site that's on our website. And you can also contact us, like I said, directly. You can contact me. And we're going to be providing blog posts and additional videos, as well as this presentation will be made available online. So as we collect questions, we're going to be responding to those and making those available publicly. So you guys will have the best and most up-to-date information on how to work with APFS. So I think that covers quite a bit. Thank you guys for hanging with us for almost an hour. Joe, I really appreciate your time in covering all these topics and our questions. And that is going to wrap up our presentation for today. We will be providing the recording at a later date. So thank you so much and have a great day.